Hey, PreCalc, here we are with 1.10, 1.10. We are talking about mathematical modeling and variation. Two types of linear models. The more general model has a y-intercept that is a non-zero, y equals mx plus b. In the simpler model, y equals kx, or basically y equals mx, just no intercept. It's said to be direct variation. Y is said to vary directly as x, or to be directly proportional to x. Okay, so the following statements are basically the same. Zoom in here a little bit. Y varies directly as x. Y is directly proportional to x. Y equals kx for some non-zero constant. Okay, those three statements are all interchangeable. K is the constant of variation or the constant of proportionality. All right, example. In Pennsylvania, let's see if I can get all this in. The state income tax is directly proportional to gross income. You are working in Pennsylvania and your state income tax deduction, or it comes out of your check for state income tax, is $46.05 for a gross monthly income of $1,500. Provide the mathematical model that gives the Pennsylvania state income tax in terms of gross income. Okay, so y equals k times x. The state income tax is directly proportional to gross income. All right, so our income tax, we got 46.05 equals some constant multiplier k times $1,500. All right, divide by 1,500, and our k value should be missed of 0.0307 or 3.07%. So that's our k. So it's going to be y equals 0.0307 times x. Another type of direct variation relates one variable to a power of another variable. For example, in the formula for the area of a circle, a equals pi r squared, a is directly proportional to the square of the radius, and pi is our constant in that situation. So direct variation as a nth power is a power here. Y varies directly as the nth power of x. Y is directly proportional to the nth power of x. Y equals kx to the n for some constant k. All equivalent statements there, ways that you might see this in your homework. The distance a ball rolls down an inclined plane is directly proportional to the square of the time it rolls. During the first second, the ball rolls 8 feet. How far will the ball roll during the first 3 seconds? All right, so we have something directly proportional to the square. So our setup here is y equals k times x squared. The one they gave me, 1 second, 8 feet. So we went 8 feet times 1 squared. Okay, so we could solve for k. We're going to get 8. So now I know y equals 8 times x squared. Plug in 3 now. So there's my equation for answers A. Plug in 3 seconds. 9 times 8, we're going to get 72 feet. There you go. All right, so it's just setting it up. There's usually going to be one where they tell you All right, where they're going to tell you the x and the y, and you have to solve for the k. So then now I can rewrite my equation with the k already in there. And then there's going to be like another part where you have to plug in x and get the y now that you know the k. All right. In 3 and 4, the direct variations are such that an increase in one corresponds to an increase in the other. This is also true in the model D equals 1/5 F, where an increase in F results in an increase in D. You should not, however, assume that this always occurs with direct variation. For example, in the model y equals negative 3x, when your k is negative, an increase in x would actually result in a decrease in y, but it's still direct variation because it follows this format of y equals k times x. So that's why they kind of go with proportional. All right, another one, inverse variation. Y varies inversely as x. Y is inversely proportional to x. Y equals k divided by x. So direct variation is y equals k times x. Inverse is y equals k divided by x. All right, if x and y are related by an equation of the form y equals k divided by x to the nth power, all right, then it's going to be an inverse relation with the nth power of x. So it's going to be the same type of stuff, it's just going to say inversely. Inversely, x is on the bottom. Some applications of variation involve problems with both direct and inverse in the same model. These types of models are said to have combined because they're using both at the same time. All right, example 5. Maybe if you've had, what would this be from, chemistry or physics? Okay, a gas law states that the volume of an enclosed gas varies directly as the temperature and varies inversely as the pressure. Okay, so volume varies, so always equals K, directly as temperature, so times T, and inversely as pressure, so divide by P. So you probably recognize that formula from your science class that you've had before. Okay, now it's going to give us all the things that we need to solve for K, and then we're going to apply that to this new one. Okay, as shown in figure 1.105, the pressure is 0.75 when the temperature is 294 and 8,000 cubic centimeters for the volume. So plug these in so we can solve for our K. The volume is 8,000. They gave it to us out of order. 8,000 equals K times my temperature was 294 Kelvin over P pressure 0.75. This is multiplication dot, not a decimal dot. All right. So maybe multiply by 0.75. 8,000 times 0.75 should be 6,000. Equals constant K times 294 divided by the 294. Now 6,000 divided by 294. And our constant K is about 20.41, 20.408. Did it say what to round to? It did not say what to round to. So here's our equation. V equals 20.408 times T over P. All right, now we can find B. Ooh, they're not asking us for volume. They're going to give us volume. 7,000 equals 20.408 times, they gave us temperature, 300. We have to solve for P. All right, so this isn't all that bad. You could multiply both sides by P, divide both sides by 7,000. What's going to happen is these two are going to switch spots. Sorry, my arm's kind of at this weird angle to get around the computer and still stay under the Elmo and write. Okay. So we got 20.408 times 200, 300. See, I almost misread my own handwriting. 300. And then divided by 7,000. And our pressure should be 0.875. We'll call it 0.875. Kilograms per cm squared. Where did you get kilograms per cm squared? That's what they called their pressure up here. That's what their label was up in the problem. So that's just what I went with. I'm sure you could break all these down and come up with the right labels. But that's just what they went with pressure up here, so that's just what I'm going to put pressure down here. All right. Almost done. Last page. In example 5, note that when a direct variation and an inverse variation occur in the same statement, they are coupled with the word "and." To describe two different direct variations in the same statement, the word "jointly" is used. So if we're going to do two direct variations at the same time, or more than one direct variation at the same time. Okay? So z varies jointly as x and y. Z is jointly proportional to x and y. Z equals constant k times xy. And you could even put more in there. If it was with a power variation, they're going to mention that is the nth power or whatever power of x or y. All right, and this sets us up pretty nicely for the simple interest formula. The simple interest formula for a certain savings account is jointly proportional. So interest is going to be jointly proportional. So we're thinking I equals K. It's always equals K. Okay. To time and the principal, the starting amount, the starting investment amount. So T for time. We'll go with capital T, less likely to change into something else later, and P for principal. Okay, after 1 quarter, 3 months, the interest on the principal of $5,000 is $43. So we got $43.75 is equal to K times time. They're talking quarters. 3 months. Let's just leave it as months, 3/12 or 1/4. 1/4 of a year. That's usually time in years, I think. Okay. And principal was $5,000. All right. So we got 1/4 times 5,000. 1,250. All right, we're going to divide that over. 43.75 divided by 1,250. .035 is our K. Find interest after 3 quarters. So now I'm trying to solve for I. I know the K, 0.035, 3/4, so I'll go 3/4, $5,000. 3/4 or 0.75 times 5,000. $131.25. All right, so there's our notes and example problems. Okay, our homework should be pretty similar along those lines. You can also check the book examples for more assistance there. All right, let me know if you guys have any questions. We'll see you in class.